Okay, guys, before we start, I'm just gonna check if my sound is okay. Okay, sounds good, so we should be fine. Let me just actually check OBS. I might be peaking a little bit, but yeah, you can let me know. So yeah, basically what we're gonna be talking today is SIMD. So for people that don't know, that just means it's like an optimization in the CPU where you can do a single instruction and do multiple operations with a single instructions, basically. So a single instruction, multiple data is what it basically means. And the idea is just using some parts of the CPU that already exist, but you by default are not using it, and basically using it to speed up some specific types of calculations, basically. And just for fun, I guess we can start out. So the reason why I just created this library was mostly, I guess, for fun. It was just an interesting thing, especially because blueprints are kind of way higher level, so you can't even do these types of things. So I had to do stuff in C++, which was, I mean, mainly vibe coded, to be honest, because I'm not gonna, do these hyper technical things when I don't even know C++ enough. But yeah, I basically created a library, tested it, tested the optimizations, and created a bunch of stuff that we're gonna go over, and basically kind of why it's important and what you can basically do with these types of optimizations, since they can be hyper performant. You're basically kind of, with these types of optimizations, you're basically peaking in performance where you're doing the most, sorry, give me a second. You're basically doing the most, you're trying to get the most out of your CPU, and when you combine it with all the other stuff like cache locality and stuff like that, you can basically get the most of your CPU, coming the closest you can to that theoretical number of, if you ever read like, oh yeah, this CPU can do, I don't know, 7 trillion operations a second or something like that. So these ways you're kind of trying to come closer and closer to that number, but the thing is that you kind of the amount of things that you can do becomes a bit narrower, or not a bit, but it becomes a lot narrower because you are now doing hyper specific operations that it's not like generalized that you can just plug in any type of like a feature or whatever into it and it's just gonna work magically. So just kind of as an example, what this does is, let's go to here. So I'm just gonna do type SIMD, and these are all of the functions that the library has, and I'm gonna go through one of the most basic ones. So basic operations, actually this would not be it, so let's do again, add vector. So one of the most basic operations that you can do is basically you have an array of vectors. So actually, yeah, I don't want to just start yapping about stuff if you don't even get kind of what's happening under the hood in the CPU, basically. So let me see how to start with this. So basically you have operations that CPU does, and you basically tell CPU, hey, let me do this. Sorry, give me a second. Why is this not working? Nice. For some reason this is selecting. Okay, cool. So this is not working. Okay, I'm just gonna take, actually we can take this. So basically your CPU has operation that it does, and this operation can say, hey, take number A, or take a value A, take a value B, and just add them together. So this operation basically says add two numbers together. Another operations can say, hey, jump to this part of the code. Third operation can say, hey, can you move this from this place to this place? And when you do these things, if I want to, for example, have 4 numbers, what I have to do is have 4 operations, and each operation can say, hey, take the first number A, add it to number B. Now we have a new number. Then another operation needs to say, add number A that now also has number B to number C. And then we need the third operation, add number C to number D, stuff like that. So you have to have individual operations for each add. And what basically SIMD does is says, hey, we're just going to take the the groups of data, and we're going to say, can you basically do one operation? And we're going to take 4 pieces of data, for example, and we're going to add some value, let's say value 1 or whatever. We're going to add this value to these 4 variables, basically. And it's just going to cost 1 operation. So that is kind of the most basic thing that you would be doing. So one kind of really straightforward thing for that is just adding vector to array. So for example, what we can do in here is we have a list of values, maybe let's say transforms, and all of them need to move in a specific way. Maybe they need to go up, to the side, whatever. We can just type whatever number is in here, and it's just going to be added to them, and it's going to be added way more efficiently than you would do normal in C++, and like magnitudes faster than whatever you could do in blueprints, basically. And just to kind of showcase the scale of this, let me see where we have this. There's just like tests that I had, but do we still have in here? Okay. I was adding stuff in here, but I can't check this. Okay. So let's do this. We have big array A, so I'm gonna check where we added big array A. So we have, is this 1 million or 100? Oh, okay, this is 100,000. Yeah, we cannot do 1 million. So basically what we're doing here is for looping with, actually even better, sorry. What I'm gonna do is showcase it in here because I created a whole map with all of the stuff in here so I can test this stuff out. So if I press play here and I go towards the classic, this just does the basic operation where we add, we just add some vector to an array, and it basically needed, so we went from 1.9 seconds, 0.2.604 to 902.907, whatever. That is basically around 300 milliseconds. It's kind of hard to see here, but actually I cannot do that, never mind. It's kind of hard to see here, but basically it took around 1/3 of a second to add 200,000 vectors to another vector array, if that makes sense. But if you do SIMD, you can't even kind of see the difference because it's like, maybe like, is it like 10 microseconds or 100 microseconds? It is so fast that just me printing this probably took more time than actually doing the 200,000 calculations. So there might be just like an error rate of calculating this much that it wouldn't even be like this this, I think it's 100 microseconds. So to kind of showcase this, what I'm gonna do is let's press play here to trace, and let's try to trace this, and then I'm just gonna quickly do SIMD one, and I'm gonna close this, and I'm gonna go to our Unreal Insights. And if you haven't seen, I already made like a video for Unreal Insights, stuff like that, how to use it. But what we're gonna do in here is let's check our time, and I think I was using, I'm just gonna go here, check. How can we trace this? We can trace this by doing searching for classic. Okay. So it should be in here to just check how long it took to do this calculation. Okay. So the classic calculation took around 300 milliseconds. So if you're talking like game frames, usually 30 FPS games, 30 milliseconds, so this took about 10 frames to calculate. The other, I think it's add vector to array. So when we do SIMD and we do it in C++, basically, it took 900 microseconds. So it's about 1 millisecond. So we went from 300 milliseconds to 1 millisecond to do the same amount of calculations. And by the way, 1 milliseconds, if you think about 30 FPS games, that's like 1/30th of a frame, basically. So we went from 10 frames to 1/30th of a frame. So this is kind of the scales that we are talking about, and this is not just we are doing something in C++ or we are doing something in blueprints. This is also the SIMD optimizations where we take advantage of your CPU. So for example, if you didn't use SIMD here, and I'm not sure, now there is like differences because different CPUs can do different like ranges. So there is like SIMD, there is like a SIMD optimizations for like 4 data 4 data at a time, basically passing 4 data at a time and then adding that. And there is some that do 8, that do 16. So I'm not exactly sure what my CPU does, but if we do this just a classical way, we just did not normal CPU thing, it will still be way faster than Blueprints, but it will probably be like maybe like 5 milliseconds, 8 milliseconds, whatever. So it will be like anywhere from like 4 to 10, 15x slower. So that's why I wanted to basically create this plugin just for me to learn kind of, and also have a little nice utility for these specific operations that I need. And as you can see here, we have a bunch of more different operations, so it's not like we are just focusing on like just adding vectors and stuff like that, so there's like more stuff. But just keep in mind, this is like very specialized. It's very specialized stuff. It's not like you can just do anything, plug it in anywhere. So yeah. So let's actually go through different things that you can do here. So first, add vector to array, pretty self-explanatory. You have like, usually this is like for 3D stuff, so I'm just gonna explain it in 3D. So you have like locations for some vectors, and they all need to move to some other location, and you need to do like mass update of their locations, of their transforms. Doing SIMD way is effectively free, while doing it like Blueprint way, you're gonna get stutters, you'll get all other stuff. Oh yeah, and just to kind of showcase kind of what's the difference. So the classical way, what you would do is you have the vectors you're operating on, you just do a simple for loop, and this could technically be a little bit more optimized. I could do like for loop, not with break, the other one. We could do something like this, and then pass in the length and maybe try like that, but we still need to like do the get like this. I'm not sure if this is faster or not. Maybe there is like some internal optimizations when you package the project or something, optimization that makes this way slower. So I have to like test that, but whatever performance gains we would get from doing it the other way would not be even close enough to come close to the actual like SIMD C++ optimization of doing this. But this is the basic way that you would do. You just get a target array on the index, you just offset the value, and that's kind of it. And if you look at the SIMD way, because we are just using this plugin, we are basically taking the array, taking whatever, however we want to offset it, and just doing it. And the funny thing is like doing this start and end time to just record what is the current time. It's probably giving it a decent error rate, because this can just be so fast that this can actually like make a difference for the recording basically. But kind of a simple thing, that's basically what you're doing. And we have, if I go SIMD, for the math operations, we have many different ones, and they are pretty straightforward. Like you divide the array with something, or there is one confusing one that I should just rename, but Hadamard multiply is just like multiplying, like it even says it's like x by x, y by y, z by z. So you're just multiplying like each with each one, and then you have like just multiplying it by scalar. So in here it multiplies x, y, z with just this one number, but the other one you can put different numbers on the x, y, and z. So it's kind of a small difference, but the naming can sound like it's some crazy thing like Hadamard multiply. But they're all pretty self-explanatory, nothing too crazy. Now the more interesting one, so basically in this map, actually, before we go to some other ones, also I have, actually let me actually show you this. I'm just gonna clean this up. Let's press play again. There is also some logs that happen, so you can kind of get the idea. So this is what type of optimization was it used for SIMD, because different CPUs can have different optimizations. So is it ARM, is it Intel's, whatever. This basically says how long it took to execute. So these like adds and stuff like that, like 100,000 multiply vectors by scalars, took like 20 microseconds. Just for comparison, to get 20 microseconds for some like simple for for loop in blueprints, you do like maybe between 10 to 100 for loops, and you already hit like 20 microseconds of usage, while in here we did 100,000 and we're hitting 20. So that's kind of the scales that we're talking about when we're like really trying to optimize something. So these like simple operations take way less, and then there is some more complex operations that can take hundreds or thousands or hundreds of thousands microseconds, depending on what we are doing. So this is also something that you can track and see. Looks awesome. Yeah, thanks, Revraitach. Sorry, I couldn't pronounce it, but yeah, I'm planning to release this soon. Probably put it to some like low price, like $5 or something. I'm not even sure, but yeah, planning to release it on Fab just for other people who have it. Honestly, I kind of made for myself just to kind of practice, and it sounded interesting because when I was searching for Fab for like SIMD optimized like libraries, there is literally zero. I don't know why people didn't. I mean, people do put some optimizations in their stuff, but there is not one that's like explicitly heavier optimizing for this thing. So I was thinking I could just like make one and post it. Why not? Especially because this not it's pretty kind of self-contained, like each function, so it's not like some crazy interconnected thing where I have like 20 classes and they all need to talk together. It's pretty kind of self-explanatory. Yeah, so to test this, actually I'm gonna do one thing. Just gonna disconnect it. This was just like first initial test, so it runs every time I press play, so we have to wait like half a second to run. Yeah, so how this basically testing area works is I can go in here, I can say, okay, I want to multiply, and then we test how long did it take in classical. Okay, 300 microseconds. In here it took like I don't even know, 1-2 microseconds. Yeah, so you can test for each of these. I think they are all kind of similar, so if we try normalize, it's probably gonna be, yeah, 300. They're all kind of the same. Oh, normalize, you can see how SIMD took a little bit longer because I think normalize does like additional calculation. But again, it's not even to the same scale, so instead of getting like 3000 or 300x increase with SIMD compared to blueprints, you maybe get like 250, something like that. Like you would get like 200 or 250 increase instead of like 300 for something like normalized, but yeah. Yeah, so other different things that we can, I guess, check that are more interesting. So let's say you have a target, this is your actor, and you need to move, I don't know, 2000 characters towards it, and they have kind of a predictable movement, it's kind of fixed, so what you can do is use this function to just quickly pull them towards the target, and there is like stuff for that, so this kind of just ticking every time you come in here, so you can kind of see what's happening. So this is one simple use for it. Now keep in mind, Unreal doesn't like, let me see how to say this. Unreal doesn't let you just move actors directly modifying their transforms. You have to go through their system, which gets expensive, so stuff like this is not kind of ideal for actually moving the actors. You're not going to get that much speed increase, but if you're using like instant static meshes or something like that, then you can use like batch update transforms plus this plugin equals profit or whatever. So there is like some other ways, so you have to be careful with Unreal, and if you're doing more like math operations, this stuff is crazy. You're gonna get so much increases in performance, it's not even going to be funny. Like if you do, I don't know, if you do stuff in Python or whatever, some other, I don't know if Python still interpreted, I don't even know, but if you're doing stuff in some other programming languages, you might get like 1000-fold increase in performance, stuff like that, where you can have, instead of like 1000 things like moving at the same time, you can have like 100,000 or like 1,000,000. But this one, so this is move points towards target. Let's find it here. Maybe I don't even have to search it, I could just get it, but this is how this function looks like. You pass in the points that need to move towards the target, you have the target location, you have the speed, so this is like basically like each time you call this, how much you want it to move, delta time, so it would be like half the speed basically, so this would be, if you're doing it each frame, delta time might be like 30 FPS game is like 0.03333, whatever, repeating, and hit radius is basically when you want it to stop, And if you need, you can do hit indices like who came to the target, stuff like that. Okay, so that's kind of simple one. I think we can see this. Let's see. Oh yeah, this just does the math. So for example, for this math, we did 1 million calculations and it did it in, what is this, 12? So probably like 1200 no, it will 1.2, it will be like 120 microseconds, I think, to do 1 million. Like just for loop, like empty for loop in blueprints for 1 million things would crash because you can only do like 300,000. And if you increase the limit, it would probably go up to like 2 seconds maybe, or 1 to 2 seconds to do it, while this does it in like, yeah, no time at all. But yeah, we're just doing some tests there. Then we have Verlet chain, so I'm just gonna pass through this. So this is just like simulating a simple chain where you have points and then these points update. Now this chain is a bit simple because I didn't want to bother creating like 1,000 point chain, but you could create like 1,000, 2,000 point chain and do some simulations like this because they can be extremely cheap. And there is like some SIMD optimization for this, basically. That's kind of the idea. It's faster even in PAE. I imagine it's even faster in actual build. So I think because this we're doing in C++, I think all of the compile time optimizations are already done. So the only thing that would get a bit faster is blueprints, but they're never gonna get even close to fast to compare. So you might get like, I don't know, let's say 300 milliseconds to do something, but when you package, maybe it's like 150 milliseconds. But then you look at these optimizations, it's like 100 microseconds, which is like still like 1,500 times cheaper instead of like 3,000 times cheaper. So blueprints would get some optimizations, but it's still uncomparable. It would be, yeah. But keep in mind, like when I'm compiling C++, I don't think Unreal does, because I'm doing like raw calculations. It's like kind of unrelated to Unreal or whatever Unreal packaging does, if that makes sense. But yeah. Make transforms from arrays. So we had 200,000 array size, but it took like 100 microseconds, I'm guessing. So that's 1/10 of 1 millisecond. Yeah, I should have did a bit better start and time. It's a bit hard to read, but yeah. So make transforms from arrays. That's basically from arrays. So that's basically all this. You get location, rotation, scales, and we all combine it into the transform. Again, stuff that can be easily paralleled, done at the same time. And also keep in mind, this is all single-threaded, so we're not using multi-threading. If your PC has like 16 cores or something, we're doing all of this on like a single thread. So yeah. Next thing, snap points to ground. So if I pass in here, it basically does a detection on the floor, and then yeah, does a thing. Now, an interesting thing here is that snap points to ground, we have to use Unreal's collision, which can get a bit expensive, but I think if we do, let me check something. I'm just gonna enable this and I'm gonna press play again. Let's see, snap points to ground. So even while using Unreal's collision system where we ray trace and do stuff like that, I think I was trying to optimize this as much as possible. So before it was a bit more expensive. I think it was like 2 or 3 times more expensive. But for 100,000 checks, we still did it in about 7 milliseconds. So 30 FPS game, 30 milliseconds. So we are doing it like in a fraction of that time. Of course, this can get rough if the game is like 60 FPS or like 120 FPS. But for 100,000 to do these checks, this is pretty good number. And you saw it but you saw it works here. So if I press play, where was it? The snapping? I don't even remember. Nope. Oh, here it is. So we have distance of 2 meters. Of course, this top one is more than 2 meters. So when we pass, that one doesn't snap. So again, we have stuff like this. And this might be good for like, if you're creating like a custom utility for blueprints and you want to have like bunch of points and all of them move or stuff like that. Also instant static meshes can use this, stuff like that. But yeah, you can instantly just snap everything to the ground and it should work basically fine. And how this looks here. Let's see. It's pretty simple. We trace distance, we have channel, we track, we have the points, we snap the points. And you can see we are working on the raw data. We're not like getting like locations directly or something and then moving the whole character. That's kind of some limitations of Unreal. For safety, they require you to do some stuff where it's gonna move it by itself. Well, not moving by itself. They're gonna do some in background internal like moving out of the characters. And at best, after I was testing it, it's like 1 microsecond to move an actor is like pretty good numbers. Actually, should I talk about this? I'm working on another plugin because I was annoyed about this. I'm working on another plugin that optimizes batch moving on vectors, where we kind of skip some stuff that Unreal does and decrease the time by like 2 to 3x to move an actor. If the actor is not needed, for example, if the actor is purely visual actor, we don't need to do collision checks, but Unreal does it anyway, so there is like some stuff that can make that faster, so I'm kind of working on that, some plugin for that also. But let me just kind of tell you about why this gets kind of complicated. So if you have one, we can use this again. If we say 1 US, so actually let me just use the writing thing. Can I get extra large? If we have 1 US, so this is how much it takes to move one character, which means it takes about 100 US, which is equal to 1 millisecond, to move 1000 actors. So if I want to move 10,000 actors, that's 10 milliseconds, right? So you can see how when we want to move hundreds of thousands or 200,000 actors, how we are getting into the into these like 100 milliseconds, 500 milliseconds to move the actors, while calculating stuff. If you saw before, like we have an array of 200,000 things, so we had 200,000 items in the array, and we moved all of this in 20 US, just like adding some value to the vector, basically offsetting it. So you can kind of see the difference where moving the actor, we would only be able in this time to move 20, but in here we can do these types of calculations. So because of that, there is some limit. So it was actually pretty good that this is actually running in like 7 milliseconds, because we are doing like checks, doing collision checks and then moving stuff, which is cheaper than actually moving the characters. But with SIMD we can only do actual vectors, not the actual movement. Like we cannot do stuff like this, set actor location. Like this costs 1 microsecond. We basically cannot do this. So just like thing I wanted to kind of cover for that. And I guess foreshadowing or something, but yeah, I'm also working on a plugin that can optimize this, where it auto figures out if your actor can be optimized to use like a faster way to move it, so then you can move the character in less time and basically increase performance. But yeah. Yeah, so we have snap points to the ground. Let's go through a few others that just to give you kind of an idea. Oh yeah, let's disable this. Just to give you an idea of the stuff basically that you can do with SIMD calculations. So this is just me kind of thinking of stuff that we could do, but there could be other uses that I just didn't include. But snap points to the ground, smooth path. So this is basically taking points and like smoothing them out. So like having like path points, you smooth them out, pretty kind of self-explanatory. Get closest actor. So if you test this, static mesh actor 27, let's see who that is. Bam. Can we actually see it? This guy. Okay, so I picked like few objects in the scene, just kind of test it, and this one is the closest, so the calculation was correct. Distance is basically 10 meters, which is pretty accurate to the distance. I mean, yeah, calculated correctly, so works fine. Compute separation forces. So this one is interesting. There is brute force and hashway. So let me explain what this does. So compute separation forces, what that basically means is, let's say we have some points. And what we are basically doing is checking, this point checks, hey, are you, how far are you from me? You're far this much, okay, I'm gonna move away from you. How far are you from me? Okay, this much, I'm gonna move away from you. How far are you from me? This much, I'm gonna move whatever, this way. And we kind of combine and it averages out that this guy moves maybe like, I don't know, like this. Let's use like some smaller thing. So he maybe at the end moves like this. And then we take this point, calculate for each one, take this point, calculate for each one. So if you have 4 points, this is 4 times 4, this is 16 checks. If you have 8, it would be 8 times 8, 64 checks. So you can see how it scales basically like this. The cost of computation based on how many points we have. So it basically quadruples amount of computations for every doubling of points. So every time you 2 times the points, you 4x the cost. So what this means, just kind of show you the scale, is if you have 1000 points, you would do 1000, so that's a million. So you do a million calculations. If you have 10,000 points, you would do, what is it, probably like a billion calculations. So you go from million to a billion, just going from 1000 to 10,000. So that is the brute force. Brute force means I'm going to take each point, I'm going to calculate with each other point and get the evaluation. For small calculations, this is extremely fast. If you have like 20 points, 50 points, 100 points, 100 times 100, that's 10,000 operations. Not that big of a deal for like C++ plus with this optimization. But if you have like 10,000 points, 100,000 points, it's gonna get rough. You're gonna get like seconds to minutes of wait time because you're just like 1000xing the amounts of operations you need to do. And then you have the hashway. Hashway is, it does some calculations before to create a hash of all of these points, which costs, so it is not good for small numbers. For like 20 points, this would be more expensive than brute force. But for like 1000 points, 5000 points, 10,000 points, hash kind of gets more constant. You do not get that scaling. You get kind of, I guess we can actually draw it in here. So if this is the scaling for brute force, for hash, the scaling is like this. So there is going to be like a portion that's going to be more expensive if it's like smaller numbers. But when you go into the higher numbers, this one like does way better than brute force. So I basically have like both of these working. So they kind of do stuff, and there is also like a limit to distance to they can move each other from, but you basically compute this. For this, let me find. Okay, let's do force. Oh no, I don't want. Actually, I do want this one. Wait, what am I doing? Oh yeah, I'm also moving the points. Yeah, I'm doing some extra stuff to visually show you kind of the difference, but this is not necessary. It's just like stuff. So what it has is basically just a bunch of locations, radius at which it's gonna detect other points, and then what is the amount of like distance it's going to make to go away from that point. And if we do the hash version, this one has grid cell size because we basically separate stuff. Can I show? Yeah, I'm not sure why. Oh my god, how did I open this? I pressed Alt G instead of Alt F. Can I draw? Why can't I draw with this? I have to check this later. Okay. Oh my god, I forgot. I think they increased performance for like C++, for Visual Studio 2026. So I'm just opening this one, reminded me how long it actually takes. But yeah, grid cell size, basically you have like a grid and you can select a specific size to which points you want to kind of hash in that grid, because if you make a grid too big, you're basically saying evaluate all of the points all over the place, but let's say 2 points are really far away and they would never like, they don't need even to care about each other, what you would do is basically just say, hey, only like in this small area, points care about each other, we need to calculate for this, but if it's like really far away, we don't care. Now grid cell size 0 is basically just saying it's going to auto calculate it for you, so you can hover kind of and see this. So it's best for like 50 or more 100 units, and we can automatically reduce with 0 basically. So there is like pros and cons for both. It's not like a hash is always better. For smaller values you want this. Then we have get points in frustum. So this is just like if you have a camera, you can just detect all of the points that are inside. So you give it like an array of locations, and it's gonna check based on the camera. So this. Let's see where it is. Here it is. So we have a list of points right now, just these 4 points. We have a view info, which is basically information from the camera. So if I break this, there is a bunch of stuff. The main thing that we care about is like location, rotation, field of view, basically probably like ortho width. So there is like few things we care about, but we basically take this data to get the I think it's called like a view matrix, to get like the area that we are looking at. Hi Ash. We're basically getting the area that we're looking at, and then we are checking if it's inside of the camera or not. And here I guess we are visualizing it, but yeah. Pretty simple function. Wait, is that it? I think we might have went through all of them. Move points towards target, velvet chain, transform, snap points, smooth path, yep. So that's kind of the general idea of it. So if you're thinking like to use this, keep in mind this is very specific stuff, and for games I would say it has limited use because we're mainly doing with transforms, and at any point you do kind of, let's say we did operations, this like a list of locations for actors. At some point you would have to, you know, take these points and then say like maybe there's like list of actors, and then you do set actor location. So you kind of have to transform it, and when you do this, that cost is going to be like 99.9% of the cost, while updating these transforms is going to be basically nothing, which is nice. You shaved off some calculations, but it's going to be limited kind of in game sense. So that's why I'm doing some other plugins for like pooling and more efficient batch updating. So then you can take this, you can take actors, and then you can do these calculations in like 3 to 5x faster. So instead of making like 99.9% of this being the cost, like actually setting the actors to the new location, we can make it like it's going to still sound high, but like way better. We're going to make it like 95% of the cost to be this. But then for some very specific stuff, these like SIMD operations can literally save you like, decrease like the cost of some calculation by like 20x, 50x, 100x easily. So if you are in that situation, I guess this plugin is nice for you, and I'm guessing it's gonna go live, I don't know, on Feb. I'm planning to add it like today, tomorrow. I still need to record the videos, like dedicated video for it, to explain all this stuff that I was covering here, but make it like 5 to 10 minute video, just going quickly through the tests and saying basically what plugin is about. And then I need to try to publish it on file, which is going to go through some process of verifying stuff, and I'm sure there's going to be like 1 or 2 things that I didn't do well, so they're going to give me feedback. I'm going to do that, so it's going to probably be back and forth for a few days. I'm guessing, how am I opening Visual Studio here? So I'm guessing it's going to take like anywhere from like 5 to 10 days, I guess, to be released. But yeah, I guess that's kind of about it. I don't know how this opened, but I guess, yeah, if you want to see kind of how it looks like, it's pretty crazy, so don't expect to be like readable here. But for example, just subtracting like vector, there is like a few things in this code. You have checks for what type of processor you're using. So if it's like oh my god, I'm blanking on it. if it's like an ARM processor, I think, is this like ARM processor? I don't know. It will use like some Neon stuff, and this other one uses SSE2. So there is like different types of SIMD optimizations different CPUs do. So then you have to separate for that, and then you have to like pack registries with your data and do this for like each loop, and then mass do operations using SIMD basically. So these things, like just simple addition is like all of this. While if you're just doing classical calculations, it'd be like, I don't know, 3 to 5 lines of code. So it gets what SIMD, yeah, I went through it in the beginning, but it basically means like single instruction, multiple data, meaning let me just quickly let you know I was doing stuff in here. So basically you can imagine a CPU doing like one operation. We take like a variable or like it doesn't matter, let's say value, we take like a value A and we add it to value B, and SIMD basically means we're gonna do with this one operation, we're gonna do 4 adds. We're gonna take this one value and we're gonna add it on 4 places instead of, let's say, 1, or maybe 8 places, 16 places, depends on the CPU, how that specific, because this is like hardware optimization, depends on how each CPU and CPU manufacturer implemented it. So you could do like, I don't know, way more of these at the same time. So you just use one operation to do like 8 additions or to do 16 additions. So that's kind of the general idea of SIMD. And yeah, I was just going over the plugin I made for these, just various functions that can help you with that. Again, they can be pretty specific. 99% of the time you're not going to use it, but if you need it, it effectively will make some calculations completely free, if that makes sense. Yeah, it is a pain. Yeah, there is like different. Sorry, again lost the word. But yeah, there is different manufacturers and architecture for CPUs that makes it that if you just do it like in a one way, then it's just not going to work on other CPUs. So what you have to do is do SIMD optimizations for different architectures, and then you also need to have a fallback if you're in some old CPU that doesn't even have any SIMD optimizations. So you have to do it in like 3 ways for each of the functions. So yeah. Curious how you shave off Unreal's actor transform operation. Yeah, I should make a. I'm still working on that plugin, so I'm probably gonna make a video dedicated to that. But just a simple kind of explanation for that is like what actors, like set actor location, what it does is you have like collision detection, checking navigation, actually moving the character, moving all of the components that are attached to the character, and what else? I don't even know. Let's say we have these 4 things. So whatever you're doing, it just has to do like these 4 things every time. So what we are basically doing is checking your actor. Let's say your actor is really simple and you only have just like one of these things happening. Like let's say you just have like a visual thing, like it's a simple box with no collision and doesn't affect navigation. So we actually can just literally move this object. We don't have to do collision calculation, we don't need to do this. So then we kind of try to hack it a little bit and just do this, because we know our actor is not going to go through a wall, lag out, or like move, and now our AI character is going through the box because the navigation is not updated. So this is basically a way that I'm kind of trying to figure this out. And you can, with this type of thing, you're not shaving, like, you do shave off some time, but it's still you can get it like 2 to 3x less expensive, but you're not gonna get it like 50x, 100x less expensive, but you can get it like 300 nanoseconds or 400 nanoseconds, which is pretty great for stuff like this. Yeah, that's why you have stuff like instant static meshes, where you can say, okay, we know that these meshes all have like the same thing, we don't have to like worry about too many things. We can just all at the same time update them, and it can take like 100 nanoseconds for each update instead of 1 millisecond, microsecond, stuff like that. Yeah, so that's one thing. Also, you have to worry about when you are updating actor locations. If you do like like if you have a blueprint node, a for loop, that's gonna get expensive. But if you have a thing where it's like we pass in actors, we pass in the new locations for the actors, and we do it all in like C++ in their for loop. We share off the for loop, we do the optimizations where we check each actor, how fast we can make this set, and then we do this in like one node. We just shaved off like, I don't know, 5x for setting the actor's location. So there is also that. Yeah, ISMs are nice, but yeah, the issue is, of course, ISMs are limited. So if you have an actor that is more complex and you have like 500 of them, you just can't use. And if you have skeletal meshes, you cannot use instant static meshes. They did implement like experimental instant skeletal meshes in Unreal 5.7, but it was so bad I couldn't figure it out. It was like unusable basically. Probably in C++ works, but in Blueprints it's completely unusable. Yeah, let me see. I think okay, we are like 48 minutes in, not too bad. I think yeah, the first stream was like 100, not 100, like 1.5 hours or something. So not too bad, but yeah. Yeah, but I think I'm gonna leave the more details for that in another video. But yeah, I just wanted to kind of cover this. It was kind of fun working on it. It didn't took too much, but yeah, the testing honestly took a lot of time because I had to set all of this up and make it kind of interesting to test, not just like you know, do a thing and maybe something pops up if we have like actual visual examples, stuff like that. But yeah. Yeah, I think that's about it. If there's like no more questions. But yeah, I did post like long time ago some plugins on the old marketplace. So hopefully Fab is easy to posting. Hopefully there is not like 1,000 things I need to do. So hopefully we can just make it work. But yeah. Since SIMD is not something typically discussed, yeah, I don't think. I mean, in Blueprints it's never discussed because you cannot do anything, and in like C++ for game dev probably not that much. For like hard level like gameplay stuff, you're probably discussing it a decent amount if you're doing like engine rendering, whatever. But like lower level stuff. But for like gameplay stuff, especially because SIMD is kind of hard to implement for like higher level gameplay stuff. You are usually not working with like 200,000 transforms or locations like that, but yeah. Yeah, then I think that's about it. Hopefully it made sense, but yeah. If you have any questions, yeah, I'm gonna post this as a video, so then people can leave comments, stuff like that. But yeah, I think that's about it.